Hello, this is Vera, and today we'd like talking about the causes of the computer vision from the causes 231 from the Stanford. This causes is about the computer vision. This lecture is about the sixth topic is training convolutional networks and the convolutional architectures. Let's have a picture overall of these lectures. There are two parts of this one. One is how to build a CNN. Another one is how to train CNN. Mm, in the how to build CNN part, they are about the four uh 4 points: the layer in the CNN activation functions and CNN architectures and weight initialization. And in the part of the how to train CNN, it's about the topic of the data preprocessing and data augmentation, transfer learning, and hyperparameter selections. Okay, let's start. Let's start it. For the first part is about okay. This is the components of the CNN. Today we first focus on the normalization layers of the function of the CNN. Okay, the normalization layers is a high-level idea of the learn parameters that can like us scale the input data. This means the normalize the input data and scale using the learned parameters. This is a very good way to let the networks more stable. One point is we need to know is the difference between the normalization layers and the image normalization. Or image normalization have another name of it is the input normalization. And for the image normalization topic, we will talking about later with this slides. And okay, let's have a look about the normalization layers. This is a function like this. The input is the n times the d. This means dimensions, and the normalized is a statistic calculated pre batches of that. We need to use the mean and the standard divisions about it, just by one bit, just calculate by pre bits. And after that, we learn parameters applied to the each sample. We need to apply the scale and the bias. Finally, the formulation is like this: y equals the scale times the x minus mean divides the standard um, divisions and the bias. And there are some different the normalization layer strategy. First one is the batch normalization, layer normalization, instance normalization, and recently comes from is the group normalization. And I think for the CNN we are using the batch normalization, the first one. And let us have a look for the next components of the CNN dropout. What's the means of the dropout? Dropout means in each forward pass, we randomly set some the neurons or nodes to 0, and we don't use that. The probability of the dropping is one of the hyperparameters, and we always in the comment we always use the 0.5. And how can this probability be a good idea? I think this is a very good way to let the networks, the models, and the networks more generalization. This means it will be performance better during the test stage. We force the network to have the redundant representation, prefers the adaptation of the features. For example, we don't like the networks know the features of oh, this is air, and this is tail, and this is the mischievous look, and without that, we let the network still can generate the final score. Oh, it's a cat, and we use this way to let the network more generalization. Another is good, and another is benefit of the dropout is it will let the model more efficient. This means we just training some of the nodes, not the whole of that. It will be have the less computations. So a dropout is training a large ensemble of the models that share the parameters, and each banner mask is one model, and if the fully connection layers with the large unit, and after the dropout, we only train the half of that. Okay, how the dropout working during the test time? The one strategy we need to remember is all the we need to add probability numbers go back to the heat layers during the test time. This is a good way to let the output at the test time equal the expectation output at the during time. Let's have a big picture of the dropout in the hallway. We will have a look. We add the probability during probability of the dropout in the training time. You can see the right area. The first dropout mask, and then we apply the second dropout mask. After that, during the prediction, the tax stage, we need to scale it during the test time. We need to go back the probability. We need to times the probability into the 100 later during the prediction stage. Okay, the next we'd like to talk about is about activation functions. And in this world, we have, in the network world, we have a very basic activation functions. Sigmoid is like this. And it squares numbers to ranging 0 to 1. But it have a very key problem. This means many layers of sigmoid will let the smaller and a smaller gradient. So what does that mean? This means you can have a look about the red part. The larger positive or negative values can kill the gradients. Many layers of the sigmoid, so many layers of the sigmoid means the smaller and smaller gradient in practice. So how we solve the last question? We can use the ReLU. ReLU is a very efficient activation functions. There's no calculation in that. It's only the OR operation in it. This means the function is like this. This means if the input number is larger than 0, we will keep the original one. If the input number is smaller than 0, we will keep all of them to 0. It's simple, right? But the problem also come from it. This function means there's no 0 centered output, and this function will die when input smaller 0. So how we solved this problem? We can use the GLU to instead of the ReLU, and we can have a look. We can have a look comparison between the ReLU and the GLU, and GLU is very nice. Have a very nice behavior around 0. Its smallness flexibilities training during the practice. But the GLU formulation is like this. X times the Gaussian X. It will bring a higher computation cost than the ReLUs. But the larger negative value can still have the gradient to 0. So sometimes we need to balance which one we use. There's overall of the activation functions, ReLU, GLU, and CLU. CLU is similar with the GLU, but the different formulation, and the difference between them is the number close to 0. CLU is more smooth, and the GLU just have a small range of to keep the negative value. Both of them will go back to 0 when the larger number, when a larger negative number. And KD ReLU is another version of the ReLU. This means we will keep the efficient operation, but we can give the function the negative values. Yellow is another way of the activation functions. The difference between them is it will be smooth when the number close to 0, but there's no 0 output when we have the larger negative values. So what activation used in the CNN? I think the GLU and the CLU also used in it. Okay, let us have a look about the CNN architectures. This is the big picture of the layers and the scores. We can have a look. More layers will bring the more scores. It's a general performance in the deep learning area. No, we can see before the 2011, all the network is a shallow network. And in the 2012, only 8 layers in there. After the 2014, the layer will become more and more, and we will indent into the deep learning area. What happened in there? Let us have a look. This is architecture, standard architecture of the VGGNet. The left one, you can see this is a basic version of the AlexNet. There are 8 layers in that, and the middle one is the VGG16. There are 16 layers in it. The difference between it comes from the AlexNet. The difference between the Alex is about the number of the stack and the number of the layers. And the right one is the VGG19. It also comes from the VGG19. The different is become the layer numbers during the last second stack. The question is why we still use small filters during that time. Before answer this question, we need to think about the question of what is the effective receptive field of the 3x3 filters. Okay, let us to calculate the number. I think it's 7. Yes, it's 7. This means what's the means of that? The stack of the 3x3 filters layers have a same efficient receptive field as one of the 7x3 convolutional layers, but deeper and more non-linear restive and few parameters. This means the 3 times the 3 square and 2 square compare the 7 square C square for the C channel per layers, and 3 is smaller than 7. So this is why we use the 3x3. And what happened after 2015? There have a revolution of the dips. We are true into the deep learning stage. And okay, let's have a look before of that. During the more iterations, the score during the more iterations, we faced a plant in the convolutional network. And how we solve this problem? Okay, we are using the residual network. What it means about the residual network? This means we add the residue from the last block into the next block. Because in the deep learning, in the general network before the residual network, the problem of network cannot have a performance with more layers. It's because more layers means losing more information. How we solve this problem? We add the last block information as the input, the output of the last block, and we apply it into the next block. So what's the difference between the residual network and the network? The difference is if it adds the residual information, residual block from the last layers, and after that we can keep the information throughout the deep network and let the network can work on the real deep learning. This is the architecture of the residual network. We also can see it also uses the filter of the 3x3. all of them also beginning with the convolutional layers. And there are different sizes of residual network. Okay, the next part is about weight initialization. How to initialization weight in the neural network layers? Okay, the function is like this. We set up a random number of the dimensions to weight of the different dimensions for initial weight, and we apply a small numbers times 8 to because we want to we want a weight to start off for a small init. For example, we times the 1.101. You can see the weight is like this. It's too small. But we want it a bigger, large. What we can do? We increase the number from the 0.01 to 0.05. But after that, we can see the weight of them is very big, and which we don't want. How we solve this problem? We will instead the 0.05 to the square to divide dimension input number, and this is a very good way to solve this problem, which is strategy comes coming. And activations are necessarily scale for all the layers. Okay, let us to continue on the training networks. First one is the data pre-processing. Yes, this is the image normalization. It's different about the layer normalization. What's the function of the image? Okay, first of all, we need to talk about where we need the image normalization. If we don't use image normalization, we will import the very large or very small, very range scale of the input image. And for the network, it is a little hard to coverage the models more quickly. And if after the image normalization, it will helpful for find the best loss, and it's good for the gradient descent. So what's the function of that? It's like this. The input, okay, the normalization pixel equals the input minus mean of the input, and divides the standard dimensions of them. Okay, next part is the data augmentation. This is one of the common part of the regularization. This means add some things, add some kind of randomness to the original, and for during the training time, and in the test time, we need to average out the randomness. Sometimes appreciate it's not specific. For example, the dropped out training time, we randomly dropped activations, and during the test time, used all the activations and average values with the p with the probability number. Another way to do the data augmentation is we are working on the image directly. We call it the transform image. For example, we give an original image, and we using the CNN to the original image and generate the another version of the original one. For example, the horizontal flips, we can flip the version 2 image from the original image. Another is random crops and scales. This means we crops the part of the original image as another version into the network. During the test time, we need to resize the image at a specific scale. It's different during the training. It's random, and for each size, we need to use a specific crops and a specific corner at the center and the flips. And another way is color filter, and we generate the contrast and the brightness version from the original one. And this is the cutout strategy. This means the set random image range to 0, but during the testing we use full time. We use the full image. Sorry. Okay, transfer learning. Let us have a overall of the transfer learning. Yes. There are different ways for transfer learning. One is for the small data set. For a small data set, we need to freeze some from the prediction models and only reinitialize the last layer of the fully convolutional net layers to training. And if the data is bigger, and we can initialize from the pre-trained models, then fine-tuning everything. With the bigger data set, it's better to train more layers. And what is the trick when the data is small or data is large? All of them we need to know is we need to choose a pre-trained data set is similar with the target data set. For example, for the very little data set, it's better to choose a pre-trained model which trains a similar data set. We can use a linear classifier on the final layers. But if the pre-trained data set is very different, okay, we need to select it more data or try to another models. And if you have a big data set, you can directly fine-tuning all model layers using the pre-trained models with a very similar data set. But if the pre-trained data set is very different, you either fine-tune all models layers or train from the 0. We have two ways to get the pre-trained models from public. One is PyTorch and one is Hugging Face. Hyperparameter selections. Okay. Step one is to check the initial loss. The step two is overfit a small sample. This means it means we just to tax it. And step three, find a linear rate that makes the small sample loss go down. And for example, we choose the 10 initial loss, 10 number of the initial loss. Some of them must cannot work. We just keep part of them which initial loss can work. Then go to the step 4. Cross the grid of the hyperparameter and train for 1, 2, 3, 5 epochs. And step 5, and next step is refine the grid and train longer. And let's look at the loss and accurate. Let's have a look about the train and the validation core validation. If the part of the it look like this, it's good, which we want, and what happened in there? This means the model cannot learning the information, learning useful information from the training set. This means we need to. This means this model is already overfitting, and we need increase regularization or got more data for training set. If there's no gap between train and validation, this means underfitting. There are two strategies: train longer, and two, comparatively use big models. And the final step is go back step 5 and refine the grid and train longer and look at the loads and accuracy. And their strategy about the grid layers. The one is grid layout, and the another is the random layout. Random layout is the best way for find the important parameters. Okay, this is some summary. We have two parts to learn from this lesson. The one is layer in CNN, two activation function in NN, and CNN architectures and weight initializations. For the training part, we will learn the data pre-processing, data augmentation, transfer learning, and hyperparameters. Okay, this is all of my class. And this is Vera. Thank you so much.